Have you ever tried building a payment service or a payments API? I've been recently trying to study the architecture behind these payments APIs and payment servers, how they are built and what is the architecture behind them. And one of the most important and messy topics was idempotency. Now, what is idempotency? Let's understand with the help of this diagram I have on my screen. Assume this client sending a payment request to the server. Okay, so the client initiates a payload and sends it to the server, and the server processes it and sends it further to the data store. Let's assume the data store to be Razorpay or some payment gateway here. Now the payment request is received by the payment gateway and processed. That is, the transaction is created and the payments are sent over to the other guy. Right. Now once the transaction is complete, the Razorpay or maybe a third-party payment service sends a response back to the server. Now it's a success response saying that the payment has been done. Now further, it's the responsibility of the server that it processes it further and sends a success response back to the client. Correct. Now let's assume a scenario where the server, once the payment has been completely settled, the server is trying to send the response back to the client and it crashes midway. Or let's say the response is lost due to some network drops. Now the response never reached the client, right? The client will assume that the payment failed or some mishap happened and caused the payment to fail. Now, according to the client, the payment was never made, but in reality, the payment was successful. It's just that the response never got to the client, or just the server crashed after the payment happened. Now, the client will ideally, in such a scenario, try to reinitiate the payment with the same payload as before. It could be an automated retry mechanism or maybe a manual trigger. Now, the client will send the same payload over to the server for processing again. Now, it is a responsibility of the server to ensure that the server does not process the payment twice. Because if that happens, we'll charge the client twice and make our whole data and system inconsistent. And that is a system failure. Now, to ensure that this doesn't happen, we need to make the server idempotent or make it such that even multiple requests of same payload result in the same server state as a single payload. A single request. Let's say the client retries the payment request again. It reaches the server. The server knows that the payment has been completed, so it does not reinitiate the payment. Rather, it directly sends a response back to the client saying the payment was successful. And that's how we ensure that we don't charge the client twice. The payment scenario is the most relatable scenario to understand idempotency in general. So let's go beyond it, beyond the sequence diagram, and go into the server details and the implementation details behind the whole idempotency. Okay, so let's take this diagram. I've just made the sequence diagram into the flow diagram to understand how can we make the server idempotent. So let's say when the client sends the request to the server, we cache it. We introduce a caching layer here. We introduce Redis or some other caching system. Anything will work as long as it helps us to cache the data. Let's say we use Redis here. And when the client sends the request of 100 rupees to the server, we will basically create a state in Redis for this client and it's set it to processing. Now processing is the value, right? Now what will be the key? How will we access the status for this particular client, or even niche down to this particular request from the client? So we need to identify each request, right? Identify each request uniquely. For that, we introduce something called as an idempotency key. Okay, what is idempotency key? Let's see. Idempotency key. So idempotency key is nothing but a UUID. Idempotency key is a UUID generated at the client side and sent over to the server along with the request. Now you can send it as a header or maybe a request param, a query param, and when the server accesses this request, we can extract this idempotency key by the server and send it to Redis. Now we have a key to uniquely identify this particular state, right? So the idempotency key itself is the key to access the state of the request. We can have something that uniquely identifies this request, and we have idempotency key, right? Now let's say the server sends a request to the Razorpay, and Razorpay sends back the success response. Now once we get the success response, immediately we can save the data to the database first and update the Redis or our caching layer to success. Along with, actually we should store a whole payload. For this example, let's store success, although we store a whole payload because we need to send a idempotent output as well to the client, right? That even how many times the client makes the same request, he will get the same response. Okay, so we save the response and the status as success in Redis or a caching layer. Now let's say this client retries this request once again. It makes the same request again with rupees 100 to the server, and with the same idempotency key as before. Wait a second. Yeah, it used the same idempotency key in the retry request as well. Now, as soon as we get the request, the server will access this idempotency key. It will first check if this transaction exists in our caching layer. If the key matches, we will basically send this exact payload, uh, just pass the JSON in it and send it back to the server. And that's how we ensure that the client does not get charged twice. Now, even further detail to look at, I have drawn a separate diagram for that to understand this whole process in even more detail. And before we get into the code, this is necessary to understand it. So while I was working on a production grade payment system, I was trying to implement this whole scenario of idempotency, but it got really messy because of a lot of edge cases that I was facing along the way, and it became difficult for me to implement this just by pure logic. So I had to dig deeper into the architecture, read a lot of articles. I did some back and forth with ChatGPT, went watching some YouTube tutorials on idempotency, and came up with this diagram for my own understanding of idempotency and a few of the edge cases as well. And to understand the code, we'll first have to understand this whole flow. So we'll understand how to implement idempotency in the first place. So we'll start with this client. Client sends a payment request to the server onto the pay endpoint. We generate a idempotency key at the client side and attach it to the payment request header. And when we initiate the payment request, the server takes the request, extracts the idempotency key, and we head on to Redis and save it along with the payload and the status of the payment, that is pending in this case, right? So as you can see, we have a payload here. This payload, actually this is not a payload, but a whole command that goes into the Redis to save the this particular payload alongside the idempotency key. So I have written a raw command for Redis to save this payload, although you won't be because abstraction exists. But I have written a raw command just to understand it a bit deeper. So what is this command here? It is a set command for Redis that sets a key value pair into the Redis database in a caching layer basically. Then I have set a few flags along with it, nx, ex, and number. So as you can see, I have written set the idempotency key that we had along with a stringified payload. Now this payload has a status pending, status code of 409, which states conflict, because if a request comes up again saying please process payment with the same idempotency key and the same payload, we'll send a conflicting message back to we'll send this conflicting response back to the client saying that the payment request is already in pending. Alright, so then we have this payload with the status of pending and a timestamp. This timestamp is there to handle a specific edge case, which we'll discuss later. Then we have these few flags. One is nx, the most important one. This ensures Redis locking for concurrency issues. Now, this is a simple scenario where a client sends a request and request reaches the server, it goes to Redis and saves, right? What if we accidentally trigger two requests at the same time because of some bug, or maybe just because the retry mechanism triggered instantly after sending the first request, or maybe some two different clients use the same idempotency key and you try to trigger the payment endpoint? How would we handle that, right? We need some locking to exist in order to prevent the other request from triggering the same payment endpoint or the same payment. For that case, we use this nx, which says set the payload only if it does not already exist for the key. That means if a key value pair already exists, if the key is already set, don't set it again. That is the point of this nx right here. Then we have this ex that states expiry of these many seconds. Yes, this is seconds, 86400 seconds, that is 24 hours. So we keep the payload for about 24 hours because that is a window that is ideal for payment retry. A payment retry can happen throughout the day anytime, so we keep it 24 hours on the safer side. Once we set the payload to pending in Redis, we continue with the payment processing. The payment processes, it succeeds, and we update the payment details to database that we have made a payment and logging and stuff, the basic flow. And then we update the Redis payload with the status success, status code 201 that we have created a payment, status success, timestamp, and a payment ID, right? So again, Redis is not a source of truth. The source of truth is our database, right? So we need to have the data in our database first, and then we update the Redis, because if we update the Redis first and then due to some failure we don't update the database, we will have a false transaction, right? Our data will be inconsistent. So that's why you save to the database first and then update the Redis. Okay, so far so good. Now this was the happy flow case, but there could be failure, right? There could be a payment failure as well. So let's assume the payment did not succeed, rather it failed. Now we can either update the Redis payload to a failure state, and log the failure to database. But that is dependent on the scenario that you're dealing with. That is not a concern about idempotency. But again, if we update this payload to failed, we are safe to proceed with the retry, right? In that case, it does not matter, because payment failed itself. We won't be creating another payment, right? It is altogether the first payment, right? Because the payment failed. So in that case, we are safe to retry. But what if the response failed after the payment succeeded? We logged it to the database, updated it to Redis, and while sending the response back to client, it failed. We sent a 500 record to client, and now the client assumes that the payment failed. He will retry. We'll basically check the Redis record and see, oh, the payment has succeeded. We send the response back directly from here. We don't proceed to make the payment again, right? Because that's the whole point of idempotency, right? Now, another edge case is the concurrency edge case that we talked about, this NX flag right here to prevent multiple concurrent requests with the same idempotency key. Now, this is a very important edge case for this whole scenario, this whole architecture, because there can be scenarios where a client might trigger this payment request twice. So to handle that, we can simply use this NX flag. In this particular case, it will basically take the first payload, extract the idempotency key, create a record, and at the same time, if the second payload comes in, it won't allow it to create another record, because consistency exists in Redis by default. As we have used this locking mechanism here, it won't allow it to set again, right? And we will send a conflicting state back to the client. As you can see, we will return a value of 409, that is conflict status, HTTP status conflict, with the same payload that we saved here. Now, now there is another scenario where, let's say, we saved the data to Redis, and let's say the payment did not succeed. It was stuck in pending, and the server crashed before the payment even happened. Now what? How will you recover it, right? Because whenever you retry this particular payment, it will always say pending, but never proceed to success. We are stuck with the status. Now this is another edge case that we need to handle. That's why we had this timestamp in the first place. Not this one actually. This particular timestamp, this expiry one, because we can make it expire, right? Or in certain cases, in certain worst cases where the server took time to get back up, we have this other timestamp as well. This was the purpose of this timestamp, that if the server goes down for a longer period, and we want a particular case where the clients that tried the payment in that particular downtime get a cooldown period. For that, we store this timestamp to give them a cooldown period of some time. But this actually won't exist in Redis, rather it will be in the database itself, because that is our source of truth. Cache will expire after some period of time. There is another edge case that is not present in the diagram itself. Actually, it was missed while creating this diagram. So this is a scenario which is actually beyond idempotency, but still needs attention and needs to be discussed. So what happens after the payment is successfully processed, but some failure occurs right at the moment of updating the database or the Redis, and we don't have any record of the payment in our system. We just have the payment done, but we don't have a active record saying that the payment was successful. Now in that case, when the client retries, it will keep on saying pending, or maybe it won't even say failure. It will just say pending, and the client will never know if the payment was made or not. It will be catastrophic, right, for the system. The consistency of the system will be destroyed. Now, how can we ensure that the payment is successful after the payment record was missed? We can introduce a new layer actually here, that is a different endpoint, where we ask the payment gateway itself that with this particular ID, do you have any payment record that was successful or at least failed, or do you have any information about this particular payment ID or order ID for some cases? So the payment gateway, if the payment was succeeded, will say yes, the payment succeeded. We can simply update our records and send a success response to the client, and the whole day is saved. Yeah. So let's hop on to code and understand all the scenarios, how to handle this in a practical situation. Although the code base I've prepared is a dummy scenario, and I even won't be using Redis, rather I am using SQLite to keep things simple, although we cover mostly everything. So let's hop on to the code and understand this further. Okay, so I've implemented the whole thing in FastAPI in Python. I've created 2 endpoints mainly to replicate the whole scenario. But before diving into the code, we should actually see it in action on Postman. So I've created these 3 tabs here on Postman. The first one is to generate the order ID, and the other 2 are the payment endpoints. I've just replicated the same twice. So first of all, generating order ID is important, because in a usual scenario in a payment gateway, what happens is, first you have to create an endpoint that allows you to generate an order ID from the payment gateway. They give you an order ID, and you initiate the payment using that order ID so that you can later fetch that record using the order ID to check the status of the payment. The other tab is the payments API, where we pass on that order ID, pass on the amount, and this is a flag I've created to trigger error. We'll see that later. And in the headers, I have created a manual idempotency key. This is a dummy key that I've created. You can pass it in the request headers, and yeah. Now let's see how this works. First of all, let's create an order ID. I've created an order ID. Okay, so let's hop on to the database, and we can see that we have a shell record of a payment, and it is says unprocessed, and we have an order ID that we received in the response. Awesome. Now, just for the scenario, assume that this payment records table is a database that exists in Razorpay. Alright, this is not a database that I control, rather the database table of a payment gateway system. And this idempotent payment status is our database that we are going to use to hold the status of a payment. So when we created an order ID, it created a shell record with Razorpay. Let's say we are using Razorpay, and this is Razorpay's database. So it created a shell record saying unprocessed and gave us an order ID. So when we process the payment, it will update this particular record. Now, as we have the order ID, let's trigger a payment. I'll use this particular order ID here, and we'll run it. And as you can see, it is taking some time. This is on purpose, and we got a success payload. Amazing. Now if you go to database, you can see a record has been created in our database as well, saying success and all the details, order ID, and we have a response logged as well, which is the same response that we got here. Now if I retry this particular endpoint again and again and again, this should not actually pay multiple times with the same idempotency key. I'm using the same idempotency key. If I trigger this again, this should not create a new record. Rather, it should just give me the same response again and again, right? That's the whole point of idempotency. So let's do it. See, now this is taking milliseconds of time, and it's giving me the same response each time. You can notice the payment ID that it has generated, it won't change, and that is because it is giving us the same response, that same stored response that I showed you in this diagram, right? So now let's go into some edge cases. Let's say now I'll have to change the idempotency key to make it look like we are triggering a different payment request, not the same one, and I'll have to generate a new order ID as well, which I'll use here. Yeah, let's now make a new transaction, and this time let's cause a failure. This particular flag causes a failure right after the payment record is generated in the Razorpay table, but not in our table. It will not update our table, just create a record in Razorpay. That means the payment will be successful, but we don't save the record. And see, we have simulated a failure after payment, but success was persisted. What does that mean? That means if we retry, what will this do? This won't try to make another payment. Rather, it will ask Razorpay, do you have a success payment record? If you do, please give it to us, and we'll send a success response to our client and save it to our database. If I hit this payment endpoint again, even with the true flag, doesn't matter, it will give us a success response because the payment is succeeded. It's just that we received a error after the payment was successful. See, I got a success payment record. That means we are adhering to the idempotency edge cases as well. Now the third and fascinating edge case is when we use two different tabs to replicate the same request, that is concurrent requests, as we talked about. So let's generate a new order ID and use that for both of these requests, here and here as well. Also we'll have to use the same idempotency key to make it appear like we are we are trying to trigger the same request from two different endpoints. Let's say for some reason the API got triggered twice. What will happen in that scenario? Okay, let's see. See, we got a message saying processing. That means the payment was not yet processed, and we got a 409 conflict. That means the payment record existed, and we were trying to reinitiate that payment, and we got a stored response that says processing. It's already in processing. You are trying to trigger it again. That can cause inconsistency in the system. So it just says processing and give us a 409 conflict status. Awesome. That means the idempotency is working as expected. Now, as I told you guys before, I'm not using Redis. I'm just using SQLite DB to replicate the caching mechanism somewhat, because it's not a production grade system. This is just me tinkering around, and I've created the system with just SQLite DB. Yeah, so now let's get into the code. First of all, we have this generate. We should go to the services first. I have created two services: idempotent payment service and the payment gateway service. Now, what are these two services? The payment gateway service class contains all the methods that replicates a payment gateway. Basically, this is a fake payment gateway service that calls payment gateways and creates a record in payment gateway, makes a payment request. This is you can assume it to be a payment gateway SDK. This is a payment gateway SDK or something. Just assume it as and this is our idempotent payment service. That is our service that we are using in our servers to create a payment status and make an idempotent call and all that stuff. That is controlled by idempotent payment service. This is our payment service. Payment methods of our server. I hope the difference is very clear. Now let's get to the routes. Now first endpoint is generate order, by which we generate the order IDs. As I've shown you, we generate order IDs. How that works is we call the payment gateway service, generate order ID, we pass in the amount and the DB session. and it generates an order ID using the time library in Python that ensures that the order ID is always unique, and we create an unprocessed shell order, right? That's what I showed you in the beginning. Now we have this second endpoint, that is the main idempotent payment endpoint, right? So how does this work? I have created dependency injections from the payment gateway and our payment service as well, so everything is crystal clear here. Now we can check the payload, what it consists of. It takes an order ID, amount, and the same flag as I shown you. So when the payment API gets triggered, we first of all extract the idempotency key here, and if it is not available, we throw an error. Then we create a DB session locally, and we have a payment object as well, which is basically the payment record that we create in our table. So if we have an idempotency key, we create a payment record using that idempotency key. And the important point here is to notice in the structure that the idempotency key is a unique field. I have created a unique index of idempotency key that ensures that no two idempotency key can exist at the same time. That ensures this particular thing, this particular flag, as we have talked about earlier, that this ensures that no two idempotency keys can exist at the same time. Awesome. So so far it's working as we had planned. So let's say two different requests come at the same time. We'll discuss that scenario later on. This whole block handles that, the integrity block. And after that, once the payment record has been successfully created, let's hop on here, processing new payment request. This is the continuation part. We have created a fake payment processing initiation. So as you can see, this is payment gateway service. We are faking payment processing. How are we doing that? We have an async IO system setup that makes the whole process method sleep for 3 seconds. Then it generates a payment ID, as I had shown you, with a timestamp. Then we create a payment record. This all is happening in the Razorpay table, as I told you. We fetch the existing payment record, mark it as success, and make the validation checks and all, and commit and return the payment ID. That's it. That's how the fake payment processing is working. Now let's say an exception occurs. We just update the let's say the payment gateway fails to process the payment. We just update our main table saying that the payment failed. It's as simple as that, and return the response to the user that the payment has failed. That is a simple scenario where the retry is very safe to do. That is so far we have not done anything about idempotency. We'll get to that now. This is the payload that triggers the error. If I pass the flag as true, it will trigger the error, and otherwise it will create a success payload and update the idempotency status to with the success payload, and so that we can send the same payload again and again, as I had shown you earlier. If we trigger it again and again, we get the same response. This is what ensures that. Okay, now to the most interesting part, this integrity block. Let's say two payment requests come at the same time. The first one will create a payment status record. Great. Now the second one will try to do the same, and we will give him an integrity error. That means no two same records can exist with the same idempotency key, right? That will cause an integrity error. We will do a database rollback, and we will try to fetch the existing idempotency payment status that we had created earlier. And if it does not exist, we throw an error, of course. And if it exists and is successful, we will just return the response. That means we have the response, it is successful, we will just simply return it. And this is how we got this again and again. Amazing. Now let's say it is stuck in processing. Now if it is stuck in processing, we should do a Razorpay lookup. We will do a payment gateway lookup to check if the record exists with payment gateway. We will pass in the order ID and a DB session. We here make a lookup to the payment records in the Razorpay table to check if the payment record exists, and if it exists, we just simply check if it is successful. We update our idempotency status to success and return the response. That's it. But let's say it causes an exception. We just return 409 conflict and processing that you had already seen. That ensures that if two concurrent requests occur at the same time, we can simply just tell it that the status is processing and all that. No payment record has been successfully settled. That's it. Now even further, in this case, if it is not successful, we again do the same thing to ensure consistency. Now let's say the payment had failed. We'll just say that the payment has failed. That's it. That's almost about it. I've basically implemented all the basic edge cases without using Redis, just using a simple SQLite DB, and yeah, that was about the implementation. So most explanations on the internet, on YouTube, were mostly theoretical or vague regarding the idempotency flow. So I built this to understand it even deeply, and you should too if you want to get deeper into understanding how idempotency works in real world. And yeah, it is not perfect, but I'm trying to get into more details and make it perfect. I will also introduce Redis later on, and I will keep on sharing the details about it. Till then, try implementing it yourselves. And furthermore, I've created this repository called server-side practicals. where I'll be adding these advanced backend practicals and system design patterns that I tinker around with hands-on, and I'll keep it on my GitHub and share the link with you guys as well through the description. And yeah, that's how I stumbled upon this idempotency flow, and this is how it actually works in the industry, except the fact that we use Redis for optimizations. You can directly use database as well, but using Redis is a add-on that makes the stuff even faster and even more precise. So yeah, so far this is my learning on how idempotency works, how to implement it in a real world scenario. Yeah, thank you so much.